This is part 3 of my talk in which I explain how deconvolution can be used as a method to process the renogram. In the first part of this talk I gave an introduction and in the second part I talked about the theory of deconvolution, explaining how it could be thought of as an idealized bolus injection renogram giving an impulse response function. I illustrated convolution and deconvolution graphically and showed how we can calculate mean transit time and subtract blood background. Now in part 3 I'm going to talk about deconvolution in practice. I'll talk about the diagnosis of Pelvi-Ureteric junction obstruction. I'll give some examples and talk about the practical considerations and the benefits and limitations of the method. So to apply the deconvolution method we need to draw some regions of interest. We need regions around the left and right kidneys as normal, and we also need a region representing blood input, and the heart is the usual place to take for that. We also need a tissue background region of interest. It's not too critical where this is drawn. It's only got to subtract a tissue background from overlying structures. The blood background will be subtracted later on. Then we generate activity time curves from each of these regions of interest and subtract the tissue background curve from the kidney curves and also from the heart curve to give us these background subtracted counts against time for left kidney, right kidney and blood. Now you'll notice that these curves have little wiggles representing random fluctuations, and that's quite normal for a study of this type. We're dealing with random radioactive decay in the radionuclide in the patient, and we know that is subject to random noise, so it's not unusual to get little wiggles in the curve like this, and it doesn't normally detract from the interpretation of the curves. However, for deconvolution, which is very sensitive to noise in the data, we will still need to smooth even these curves like this to get rid of even these small amount of wiggles. Otherwise, the noise will be amplified and the result will be meaningless. So smoothing is critical to this. Having got the smooth curves, we can apply deconvolution of the blood curve with the left kidney and the blood curve with the right kidney to give the impulse response functions for left and right kidney, which look something like this. I think it's important to display these response curves. Some computer analysis programs will give you the numerical results without actually displaying the curves. But in my experience it's worth displaying the curves, then you can see whether the curves look sensible, and if they are you will be able to have confidence in the result that it gives. But if you don't look at the curves you don't really know whether the numbers make sense or not. Now you'll notice that the curves don't look quite as nice as the nice theoretical ones that I showed you, which were nice and smooth. There are indeed some wiggles in these curves, which is what's left of the noise, even though we smoothed initially. So if we don't smooth enough, we will find that the wiggles go all over the place and the result is totally unbelievable. If we smooth too much, we can lose detail in the curve, so it's crucial to get the right amount of smoothing. The first thing we can do is to remove blood background. Theoretically, I said there should be a plateau with the blood background just a spike at the beginning. You can see here that in fact the plateau is not quite so easy to determine. Here we can make out the plateau for the left kidney and extrapolate that back, so everything above that is the blood background for the left kidney. And here we can see the plateau for the right kidney, and everything above that is the background for the right kidney, which we can remove. But you can see if we had too much smoothing it would be very easy to lose this point of inflection and not be able to find the plateau at all, which is one of the reasons why smoothing is critical. We also note that because this is the response to a bolus input where activity comes in at the beginning and then leaves, the retention function should always decrease. It should never go up. So we can trim off these little wiggles to make sure that it is a function that continues to go down and never bounces back up again. And that gives us these nice trimmed curves representing the impulse response functions for both kidneys. Now we can take some measurements from that. First of all, we can note the initial height here of the left kidney and of the right kidney represents the relative uptake in those kidneys. So we can work out the relative function. You can see here that the left kidney is 41% and the right 59% from the relative heights of those initial plateaus. We can also calculate the mean transit time, and you can see for the right kidney here it's round about 5 minutes. The computer says it's 4.9 minutes, whereas for the left kidney it's much longer. The mean is somewhere here round about 10 minutes. Now you could deduce a lot of that information from the raw Renogram curves. If we look at the left kidney curve on the raw curves, you can see that the uptake is not as good as the right kidney, which is being quantified once we got the deconvolution result. And you can also see that the right kidney empties more quickly than the left kidney, and again we get the numbers from the deconvolution result. So deconvolution, as well as being a method of subtracting blood background, gives us a good measure of the relative function, as well as putting a number on the transit time to quantify it. So those are the benefits of deconvolution. Now, one of the main clinical applications of using deconvolution of the Renogram to calculate transit time is in the diagnosis of Pelvi-Ureteric junction obstruction. So let me just say a few words about that condition. In the kidney we have the renal parenchyma, which consists of the cortex and the medulla in the outer part of the kidney, and this contains the renal tubules, which are just long narrow tubes. So the time it takes for a molecule of radiopharmaceutical to pass through them, the parenchymal transit time, is fairly constant and is about 2 minutes in the normal kidney. But the collecting system, which comprises the calyces and the renal pelvis, before it drains down through the pelvi-ureteric junction and then down the ureter, the renal pelvis is surrounded by muscles which have peristaltic waves, contractions, which squeeze the urine through the renal pelvis, through the pelvi-ureteric junction and then down the ureter. But the renal pelvis has quite a significant volume, so there is a mixing chamber effect here, and the time it takes for a molecule of radiopharmaceutical to pass through the pelvis depends on its volume. So if we've got a dilated renal pelvis, a large volume pelvis as shown here, and this is a condition often called hydronephrosis, just meaning a large dilated collecting system, the muscles here may have lost their tone. They're hypotonic, meaning that they're more relaxed than normal, and so we end up with a large volume pelvis, and that volume being larger will increase the time it takes for a molecule to get through, and so it increases the pelvic transit time. Now that's not a problem as long as it's a low pressure, because it won't affect the renal tubules in the parenchyma, so we get a normal parenchymal transit time. However, in the case of PUJ obstruction, Pelvi-Ureteric junction obstruction, we can have a constriction here at the Pelvi-Ureteric junction, which may be some narrowing or some abnormal muscle or loss of peristalsis at that point, or may even be due to some external thing pressing on the ureter. In these cases the pelvis will not be able to empty and will end up with a high pressure inside the renal pelvis. That will cause the pelvis to dilate, and that pressure can back up into the parenchyma and slow the flow through the tubules as well. So we can end up with a long parenchymal transit time in that situation. Now that may require the patient to have a pyeloplasty, an operation to relieve the obstruction, because if it's left with a high pressure for too long, that will damage the tubules. So diagnostically we need to distinguish the system which is not obstructed, which is a large volume with a low pressure and a normal parenchymal transit time, from a system which is obstructed, which has a large volume but a high pressure with a long parenchymal transit time. So although it's the pressure which causes the damage, we can distinguish between the not obstructed and the obstructed system by looking at the parenchymal transit time. So to calculate parenchymal transit time, we need regions of interest and curves for the heart representing blood input, for the whole kidney, which has to include everything including the renal pelvis, and then just the renal parenchyma, which excludes any dilated calyces and the pelvis. So we have a region of interest just round the rim of the outer part of the kidney, because this is got to try to measure the transit time through the parenchyma only, so we need to exclude all of the collecting system and the pelvis. We also need the tissue background region, and then we subtract the tissue background from the kidneys and heart curves as normal. Now we apply deconvolution twice. We can apply deconvolution to the whole kidney compared with the heart, which gives us the time for tracer to travel from the blood through the whole of the kidney, but also by taking the parenchymal curve with the heart, we can calculate the parenchymal mean transit time, which is the time taken for tracer to travel from the blood through the parenchyma only, that is down the tubules. What we then do is to calculate the transit time index by subtracting the minimum transit time from the mean transit time. Now, the transit time index is a concept advocated by Keith Britton in a chapter in his book Clinical Nuclear Medicine. You take the impulse response function shown here and you start by getting rid of the background by extrapolating the plateau. Then we can calculate the mean transit time somewhere here on the graph. Then Keith Britton says you should look at the minimum transit time, which is the shortest time it takes for a molecule to get through the system from here to here where the plateau ends. And then Keith Britton defines the transit time index as the difference between those, this time there. So according to Keith Britton, it's important to subtract the minimum transit time from the mean transit time. Now, the mean transit time is quite straightforward to calculate reproducibly despite some of the wiggles in these curves, but in my experience the minimum transit time is much harder to determine reliably, but it depends on determining the end of this plateau reliably, and that seems to be subject to many more fluctuations due to variations in smoothing. In my experience, it's much harder to determine this transit time index than it is just to determine the mean transit time. So I'm afraid I tend to just use the mean transit time rather than this transit time index. But if you follow Keith Britton's methodology, you should be subtracting the minimum transit time. So to diagnose Pelvi-Ureteric junction obstruction, according to Keith Britton's method, you look at the whole kidney transit time index, which in a normal should be between 20 and 170 seconds. And if it's increased beyond that, then that's what Keith Britton says is an obstructive uropathy. That indicates slow passage through the whole of the kidney, and that may just be a dilated renal pelvis. But if you look at the parenchymal transit time index, in a normal that should be between 10 and 156 seconds. And if it's increased beyond that, that's what he calls an obstructive nephropathy, and that indicates a slow passage through the renal tubules, and that's an obstructed system, showing that the parenchymal transit time is increased, not just the whole kidney transit time. Here's an example of a system that's not obstructed. Here is a Renogram, and you can see for the whole kidney, the kidney didn't empty. This patient, we gave a diuretic Frusemide for a diuresis Renogram. Diuresis renography is something I talk about more in another of my talks in this series, but for now let's just say that after administration of the diuretic, the whole kidney immediately empties. So we see that although the kidney didn't empty before Frusemide, the fact that it washed out well after Frusemide implies that it's not completely obstructed. It's just a large dilated renal pelvis. We can also draw the region of interest over the parenchyma, as I said, and we get a curve like this, which does empty. So that's indicating that there isn't actually any hold-up in the parenchyma. If we apply deconvolution, we can get the impulse response function for the whole of the kidney here, and we see we have a curve that goes on for a long time, and we can see that the mean transit time here is something around about 10 minutes. In fact, we have to say it's greater than 10 minutes because the deconvolution of the retention impulse response function hadn't fallen to 0 even by 20 minutes, and that's because we had to stop the deconvolution process at 20 minutes. One of the requirements for deconvolution, you remember, is that the flow rate must be constant, and after we've given Frusemide here at 20 minutes, the flow rate certainly isn't constant. So if we carried on deconvolution beyond the time of the Frusemide, the results would be totally unbelievable. So we have to just stop the calculation at 20 minutes, which means we never quite got the retention function for the whole kidney down to 0. So we can say it's at least 10 minutes. The parenchyma curve, when we apply deconvolution to that, we see that's got a very quite normal transit time. In this case, it's only 2.7 minutes. So whether we look at the transit time for the parenchyma, saying that it's normal, or we look at the curve for the parenchyma showing that it washed out, or we look at the response to Frusemide, we can see that this is a non-obstructed, dilated, low-pressure system. Here's an example of an obstructed system. We can see here the curve for the whole kidney goes on up and up and up, and even after Frusemide it doesn't empty, and that indicates that this is an obstructed system that is not emptying even after Frusemide. And when we draw the curve for the parenchyma, we see that that also carries on and doesn't empty. So that also indicates there's a problem with the parenchyma even before we apply deconvolution. But when we calculate the impulse response after deconvolution, we can see that the whole kidney transit time is also long. We also had to stop here at 20 minutes because we couldn't carry on after the time the Frusemide was given. But in this case, the transit time for the parenchyma is also long. So whether we look at the increased parenchymal transit time, or the fact that the parenchyma curve doesn't empty, or the fact that the whole kidney curve didn't empty after Frusemide, that leads us to the conclusion this is an obstructed system. So let's think of some of the practical considerations in order to apply this technique. We need to draw a suitable region of interest for blood input into the kidney. Naturally, the aorta would be the logical place to take for that, but if we draw a region of interest over the aorta, it's going to be very small and not have many counts, and therefore be rather noisy, and that's not suitable for deconvolution. So in most cases it's practical to take a region of interest over the heart, which is going to have more blood, more counts, and therefore be less noisy. But if we use the heart, we have to realize that there's going to be a small time delay between activity appearing in the heart before it enters the kidney, and if we don't make an adjustment for that, that can cause problems with the deconvolution process and cause oscillations in the data. We also need a suitable region of interest for kidney contents. The whole kidney is very easy to draw, and as long as the region is big enough to include all of the kidney, it can even be a bit bigger than the kidney region to allow for small amounts of patient movement during the study. But we also need a region of interest over the renal parenchyma, that's the cortex and the medulla. So it's just going to be the outer border of the kidney, excluding all the calyces and renal pelvis, because we don't want activity from the collecting system to contaminate this region of interest. So that's going to be a much harder region to draw. It's going to be just a thin border around the outer part of the kidney there, and that's not going to be easy, particularly if the patient moves, because we don't want any of the calyces moving into that region of interest. We also have to remember that the kidney is actually a three-dimensional organ, and all we're looking at here with the gamma camera is a two-dimensional projection of that. So in reality, the parenchyma extends in front and behind the renal pelvis, so all we've drawn here is part of the parenchyma. Now, if all we want to do is to measure transit time, that's okay, because the transit time through this part of the parenchyma is representative of the transit time through the whole of the parenchyma, so a transit time measurement will still be valid for this region. But it won't be any good if we want to measure relative function, because the counts in this parenchymal region are less than the total counts in all of the parenchyma, so we will underestimate the activity in the kidney. So although we can use this parenchymal region for transit time, it's no good for relative function, and we still need a whole kidney region in order to measure relative function. Now, in the theory part of this talk, I explained that one of the assumptions that we needed for deconvolution to work was that the system must be linear. Now that's okay, because the concentrations of radiopharmaceuticals that we encounter during renography, the kidney never reaches saturation. So if we double the activity in the blood, it's reasonable to assume that the activity in the kidney also doubles, which means we have a linear system. So this is a valid assumption. However, we also assume that the system must be stationary, that is, its function doesn't change with time. So we mustn't have any sudden pelvic contractions. You can sometimes get a renogram in which the kidney, the renal pelvis gradually fills and swells up and up and up, and then after a few minutes it suddenly empties in one big spurt. And that gives a renogram curve which comes down in steps rather than smoothly. If you have a renogram like that, it clearly isn't stationary, it is changing with time, and so you couldn't get away with applying deconvolution to a renogram like that. However, normal peristalsis is okay because it occurs rapidly enough to be averaged out within the time frames of the normal renogram, and so it's not going to affect that condition of stationarity. However, one other problem is that we can't give Frusemide. Frusemide is a diuretic which greatly increases the urine flow, and so clearly that changes the condition over time. So if we give Frusemide during the renogram, we can't use deconvolution at any time after we've given Frusemide, because it would violate this condition that the system must be stationary. So let's see how the urine flow rate changes after administration of Frusemide. ISCORN, that's the International Scientific Committee on Radionuclides in Nephrurology, produced a report on renal transit time measurement in 2008. In that report they reproduced this graph showing how the urinary flow rate changes after administration of 40 milligrams of Frusemide intravenously. They showed that after 3 minutes the flow rate increases quite rapidly and then begins to level off, and by 15 minutes is reasonably constant. So ISCORN used that to say that although you couldn't apply deconvolution immediately after Frusemide, 15 minutes after Frusemide, the flow rate had reached a constant value, and implying that you could therefore use deconvolution. So the F-15 technique, where you give Frusemide 15 minutes before the start of the renogram, could be used for deconvolution because the flow rate would be constant at 15 minutes after the Frusemide. Now, the data that they show in this graph actually came from an earlier report by Steve Brown, Steve Upstill and Paddy O'Reilly, published in the British Journal of Urology in 1992. Now, I know that that work was actually started earlier by Steve Upstill when he was working in our department in Manchester Royal Infirmary. So I've looked in his MD thesis, which was published in 1989, that includes some data, 17 patients who was a subset of the data published by Brown that appeared in the ISCORN report. So here is Steve's analysis of the average of 17 patients, where once again you can see that after the Frusemide the flow rate goes up quite rapidly, and once again it looks like it's constant after about 15 minutes. But that is the average of 17 patients. If you look at the individual patient data, you can see that there's a lot of variation. In some patients it had hardly changed by 5 minutes and went up quite rapidly after that. In others it was quite high at 5 minutes and fell over that time. So if you're trying to say it should be constant flow rate after 15 minutes, you see that individual patients, there are some here where the flow rate goes up after 15 minutes, some where it went down quite considerably after 15 minutes. So I think the variation between individual patients shows that you would be uncertain to be able to be sure that the flow rate in an individual patient was constant after 15 minutes. In some patients it might be, in others it clearly goes up, and others it comes down. So in my opinion, it's not adequate to say that it's safe to assume the constant flow rate after 15 minutes. Therefore, I don't believe it's safe to apply deconvolution at any time after Frusemide. More practical considerations to think about. We need adequate time resolution. A Renogram acquired at 10 or 20 seconds a frame is okay. If you go any longer, 30 seconds a frame probably is too long for deconvolution, but that's probably acceptable. All Renograms can be easily acquired at 20 seconds a frame. You need the correct start time. The Renogram needs to be started at just the right time when activity appears in the kidneys, and if the time delay between activity appearing in the heart and then the kidneys, that can cause some problems, and you may need to apply a little shift in time to allow for that. We need good statistics because we don't want too much noise in the curve. So you need to give a higher administered activity than you might otherwise do for a Renogram in order to minimize the noise, and even then you must smooth the curves by just the right amount. We have to remove background. The non-vascular, the tissue background, can easily be removed using a separate tissue region of interest, and the vascular is removed by looking at the early points and finding the plateau and extrapolating it back, as I said. The benefits of deconvolution are that the result doesn't depend on the shape of the blood clearance curve. So it's independent of how rapidly we give the injection. It's independent of non-renal clearance by other organs, and indeed of clearance by the other kidney. It permits removal of vascular background by extrapolating the plateau of the response function to remove the initial spike where the vascular background is concentrated. And it quantifies the kidney uptake from the initial height of the response function, so we can get an accurate measure of relative function from it. Most importantly, it quantifies elimination using the mean transit time and gives us a number for the mean transit time. It's therefore quite useful in the diagnosis of Pelvi-Ureteric junction obstruction, as long as we can define the parenchymal region of interest to get the parenchymal transit time as well as the whole kidney transit time. The limitations of deconvolution include the fact that you need to administer a larger activity. You need to give at least 100 megabecquerels of technetium mag3 in order to get enough counts, in order to get good statistics to apply deconvolution, whereas a standard Renogram can use less activity. In Manchester, we routinely use 50 megabecquerels of mag3 for a standard Renogram. You need care in defining the regions of interest, particularly the parenchymal region of interest, which needs to be very carefully drawn, particularly a problem if the patient moves at all. You need optimal smoothing. If you do too little smoothing, you end up with noisy data, which ends up with oscillations in the response function. If you do too much smoothing, you have difficulty in identifying the end of the plateau. It's very sensitive to small errors in the data, so noise, too few counts, patient movement, or time delays between the heart and the kidney can sometimes produce silly curves. So it's important to always look carefully at the results to make sure that the results that you get are believable. Also, as I explained, you can't use it after Frusemide because the system is no longer stationary. So for all of those reasons, it can't be applied to every Renogram. There are always some Renograms where deconvolution will fail. For that reason, I've always regarded it as a research tool to be used in addition to standard renography if you want some numbers from the transit time. But in Manchester, our routine doesn't include deconvolution as the standard. If we're trying to diagnose PUJ obstruction, we prefer to use diuresis renography, which is the subject of another talk in this series. So in summary, deconvolution uses the real Renogram to predict what the Renogram would look like following a perfect bolus injection. It produces something called the impulse response function, where the initial spike represents blood background, which can therefore be subtracted. The plateau height is a measure of kidney function, so that can be used to determine relative function. and the duration measures kidney transit time. But it needs good quality data and care in drawing the regions. And if you're administering Frusemide, then the results should be treated with caution, because it can upset the calculation. So if you found this interesting, there are more of my Renogram talks. I have one on models of the Renogram, which illustrates several different models of the Renogram. One explaining how to process a Renogram, where to draw the regions of interest, how to achieve correct background subtraction, and how to quantify relative function and elimination. I've got one on how to display a Renogram, which includes how to quantify absolute uptake and how to allow for different kidney depths. I've got one which explains how the Rutland plot or Patlack plot works, which gives more details about the Rutland method of background subtraction. And I've got one on diaresis renography, which explains diaresis renography and compares it with the results of mean transit time calculation by deconvolution, which I've just been talking about. So all of those talks are available on my YouTube channel.